In this video, I want to introduce how symbol tables are used in compilers. Now, compilers are a very, very complicated topic. Typically, people consider compilers to be like the rocket science of computer science and software engineering. In order to work in compilers, you basically need to know everything, right? You need to know, algorithms, data structures. You need to know hardware level stuff. You need to know operating system level stuff. You need to know optimization stuff. You need to know tons of math in order to show that things work the way they're supposed to do. You need to know absolutely everything. So for now, we're going to give you guys just a really quick glance at how this stuff works. Or at least, I guess, a portion of it works. So let's check this out. So let's take a look at that function on the right-hand side. So here I have something called compute z. This is a function. This is something that you would write, right? And you would be happy, right? You write it, you can compile it, you can run it, you get back the result. Life is good. The problem is, though, that somebody actually has to take care of that process of, I have my computer code, or my user-written code, I need to convert it to machine language, right? So that's a non-trivial thing to do, right? There's a ton of work that has to happen. So one thing that happens during the compilation step, and there's various reasons for it, is the compiler actually looks at your functions and it tries to figure out what are all the variables that are there. So here I have x, y, and z. And from those variables, it constructs what is called a symbol table. So actually, right, there's kind of this naming symbol table is actually used twice. So it's not just the name of our data structure that we're inventing right now, we're going through, it's also the name of a specific data structure inside of compilers that stores variables and functions. So here, right, this is a symbol table, right? It's not just literally like this table that we've been talking about before where things are paired up. It's actually, right, literally this is a data structure that's constructed inside of the compiler. So the compiler looks at all your code, picks all the different variables, and makes an entry, right, into its symbol table for everything it finds. In each entry, what you have is you have a variable name as a key, and then its value is basically an expression, right? So it's like whatever I assigned that variable. Because the compiler basically needs to know what is it that's out there, right? If it's compiling, it needs to know what are the variables that are available. There are a few places that we use this table. So one would be, for example, if you guys know, for example, the call stack, right? So this idea of, I make call functions. Every time I call a function, I need to request memory to store that function. Well, how much memory I need to store? That's actually computed by the compiler, because the compiler looks at your functions, sees how many variables you have, and says, okay, you have 3 integers. That means I have 96 bits of data that I need to store. It can calculate that, right? It can calculate how much memory I need in order to run this compute z function, and that's going to be calculated, right, by looking up what's available in that function from the symbol table. So that's kind of the first usage of having this thing, right? Just knowing how much memory something takes, so that I can request the memory when the user wants to call the function. So that's one usage of it. Another usage is something called value propagation. So value propagation is actually an optimization technique, because one of the big parts of compilers, right, so compiler maybe does two things in a sense, right? One is it converts from your handwritten code into machine code, right? That's a big deal. But then it also applies a bunch of optimizations, right? Optimization is actually the main trickery in compilers. So moving something from written code to machine code isn't so bad, because program languages are reasonably similar to like a CPU instruction set. There's all sorts of syntactic sugar on top of it, but it's not too bad. Where you get into more trouble is when you look at users' code and you want to make it faster. You want to rewrite it, you want to optimize it in a sense. That becomes very, very difficult, because if your compiler is optimizing the program that it's compiling, then it needs to be able to optimize it in a way that doesn't break anything, right? We don't want to all of a sudden change the user's code in a way that it gives you a bad result, right? Then the compiler is a bad compiler because it's not doing what it's supposed to do, which is convert the program to machine code. So optimization, right, really is the higher area of difficulty or complexity in design compilers, and that's all of a sudden and that's now going to be what we start talking about. So yeah, so in general, right, what we have here is a symbol table is basically a way, right, to work with variables. It's a way to work with the expressions that are assigned to them. So value propagation. So let's take a look at this. So again, we have this function, right, compute z. So imagine, right, that we first go through this and we basically have a symbol table, and we fill out the different values in there. Okay, so we have x, y, and z. Now, I guess before I go down and talk about the rest of the stuff, let's maybe jump back up to our program code. One thought about this might be, right, if I look at this code and I have to think to myself, hey, is there any way to make it faster? One thing I might start to think about is basically that some of the work here, right, that normally would be done by the program when it runs, could be done a little bit earlier. Okay. So normally if I have this program, I can compile it and I run it, right, I'm going to have to create 3 different variables in memory. I'm going to have to do 2 additions and a multiplication, right, and all this will happen at runtime. So every time the user runs this program, every time different users run it, it'll always compute the same thing. Now, if I were, though, to basically give this to somebody and ask them on paper to make it simpler, they could probably do that, right? Because I know x, because I know y, I could actually evaluate z and put in z in that println. So I could actually know the number in advance. And this would actually be a very nice thing to do, because if we had our math all figured out in advance, that means I could build my program, I could send it to different users, and then those users would have to pay the computation cost of having their CPU do this addition and this multiplication again, right? We want to be able to save them time. We want to do this pre-compute step. In general, right, it's basically what you want to aim for, right, is that if you can do work at compile time instead of doing it, making the user do it, right, when they run the program, do it that way, right, because you're going to save them time. You're only going to compile once, right? And then if you compute it there, well, anybody that runs your program, right, and there could be 100 users, right? It's like that result is already there, right? You save 100 users just a little bit of time. Now, I know it's just a little bit because I only have 3 lines here, but you can imagine if you have more complicated expressions, you can save a lot more time. So what we want to do is basically we want to find a way to automate this, right? We want to be able to find a way to automate automatically evaluating expressions when we know all of the operands of it. The name of this technique in general is called value propagation. So now we know what we're doing. We'll jump back to the right-hand side. All right. So I said before, right, we have our table here. We filled out our different variables. We have 3 of them, x, y, and z. So what we can kind of imagine is this, right? If we want to mimic this process of figuring out those values in advance, we're going to look through our code and basically write in any constants we see. So I have some rules down here. So if right-hand side is a constant, store the constant. So these rules are basically the things that the compiler would follow if it was parsing through your source code and trying to simplify it. If it was trying to do value propagation. So it's actually going to take that 2 and like move it to the other places where that x is. That's what it means when we say propagation. Like we're moving values for it. So looking at our rules, right? If we're kind of parsing through our program line by line, trying to make it faster, we can basically look at our variable and say, oh, hey, this is storing a constant, so I'll go ahead and save the constant in my symbol table. And so that's what I've done over here. Then I go back and look at my next line. So y equals x plus 5. And I could try to store, x equal 5 or x plus. Excuse me. I could store x plus 5, over here. Right? I could try, something like that. Or I could store the expression, and that's typically what a compiler does. But for this optimization technique, we want to do a little bit better. We want to basically say the following: before I store that into the symbol table, check to see whether there's any variables in the symbol table that have values which are constants, and if they and which are used in that expression. So I have x plus 5. Hey, x does exist in my symbol table. X's value is a constant, it's a 2. Maybe I can substitute it in there. And so my x plus 5 actually becomes 2 plus 5. If I'm left with an expression that's all constants, evaluate it. So I get back a 7. Okay? And so then I can update my table. And so I have this over here, where all of a sudden I have now y is in my table, and it's now associated with 7. So I've propagated that value of x forward, right? I wrote it down initially, now I went to y used x. I've inserted that value 2 for x, and now I'm able to actually get a number back, a constant back for y. Okay? And so I can do this again. Right? And so now I have z, right? Z follows the same rules. So initially I start with y plus x times 2. I can go and I can look up y and x inside my symbol table. Hey, both those are constants. Do the substitution. Get 2 plus 7 times 2. It's an expression with all constants. Evaluate them. 19. And so then this occurs over here. So now we have basically a constant for z. Now, depending on how the compiler works, right, there's actually other stuff you can do as well. We've already, though, saved kind of a lot of time. In our code, right, when we go basically to to generate the program code for this thing, you can imagine that all my additions and all my multiplications basically can be thrown away, right? I have my 2, 7, and 18, right? I have all those constants figured out, so I don't need to do any of that work. And actually, right, in a more advanced compiler, what would happen is it would say, oh, you know what? X is not used anywhere, right? Once I've done that propagation, right? Because after the propagation, right, this code basically gets rewritten, and instead looks like this. It looks like 7, 18. Right, so those are now assignments, and they can actually look in there and say, "Hey, x isn't used anywhere. Get rid of it. Y isn't used anywhere. Get rid of it." Right, and I can save those I can save having to pay the cost of processing those variables as well. I end up just with my z equal 18, and maybe even there would be another pass which basically goes and gets rid of z and just replaces the 18 right over here in println. So yeah, this is value propagation. So the idea, right, is we have a symbol table that's basically monitoring all the different variables in my program, and I'm using it, right, to basically do these substitutions where it's like, well, if I have constants, I can keep track of them. When I substitute them in and get a new expression that has some work going on, but it's all constants, then I can evaluate, I get that simpler result. Okay, so that's overall what our value propagation was doing. So value propagation is a pretty common technique in compilers. Obviously, there are many different optimization techniques. This is just an example of one, and it's kind of the one where our ideas or I guess our base ideas, right, of a symbol table are really coming from. So that's kind of it for our example. Now we're going to move on and go back to talking about kind of the generic view of symbol tables.